Hey everybody. All right, so for these notes, this is what you missed on Monday, or if you just need to hear it a second time. This is section 2.2.1. So we're talking about density curves and the empirical rule. So density curves are basically the umbrella of what we're talking about this chapter. Both normal curves and then what we're going to get ready to talk about are uniform density curves all kind of fall under this umbrella. And then the empirical rule, the 68, 95, 99.7 rule, is a nice to know, like it's a shortcut and can help speed things up for you so you don't have to do full calculations, but it's not something you have to memorize. If you can use the shortcut, great, but if not, you can always do the calculations that we talked about in class on Tuesday. So a density curve is just a fancy relative frequency histogram. All we do is take those bars and we smooth it out so it looks like a curve. Although sometimes it doesn't look like a curve. Sometimes it looks like a rectangle, and we'll look at examples of those. So a couple things you want to know about a density curve. The area under the curve is always equal to 1. And the ones that we're going to draw are always in the first quadrant. So some folks that have either had AP Calculus or are going to take it later, you'll be dealing with these density curves in other places on the coordinate plane. For us, we're just dealing with the first quadrant. And then a couple of quick reminders. These problems will jump around asking for percents. They will ask for percentiles, and then they will ask for proportions. So just wanted to remind you the difference between those. It is important to pay attention to what the question is asking for. So percent is out of 100. Your proportion is usually going to be a decimal. Every once in a while you might see it as a fraction. And percentile is just the percent without the percent symbol. So pretty straightforward. So what we're going to look at first are just two random examples of density curves. I won't ever ask you to create one of these. They will already be made for you. At most, you'll just have to use it. And that's it. So the first situation we're talking about here is if we roll a six-sided dice, or a six-sided die, and we write down the number. So what this relative frequency histogram would be is how many times do we get a 1? How many times do we get a 2, a 3, a 4, and so on. Because it's relative frequency, that's talking about percents. So in this case, I wrote it as a proportion instead of a percent, but it works either way. And if a die is fair, meaning it's not weighted, each side should come up the same amount. Now, in reality, we know that's not always true. But if you roll it enough, that's what it will come out to be. So what we have on the left there is our relative frequency histogram. Pretty straightforward. That's what we did back in the last chapter. So a density curve that matches that would be taking that same shape and getting rid of all the bars. So in this case, it's just a rectangle. At least it should be a rectangle. That's a little wibbly, but you get the idea. That's all it is. It's just smoothing out the breaks, and we're just looking at the entire space where these could occur. So that's a density curve for, this is what we're going to talk about in a moment, would be a uniform density curve, meaning everything is equally likely to happen. Everybody has the same probability. So this second example is when we have a stopwatch and we're trying to stop it right at 5 seconds. So if you've ever played with a stopwatch, either on your phone or an actual handheld stopwatch or one on your watch, you know that it's really hard to get it to land right on the time you want. But if you practice it a bunch, you can eventually start to do it with some success. So this histogram here is assuming we've done it for a while. And so we've gotten to the point where we eventually are able to get 5 pretty consistently. But on either side, you can see where we tried. So we have some evidence of we were too low for a few times, we were too high for a few times. So this type of graph is symmetrical. And when we draw a density curve for that, what it's going to look like is we want to smooth it out. We want to get rid of the bars. So we're just going to kind of mimic the shape. And I was telling everybody in class that I really kind of are not great at drawing these. The good news is On the AP exam, they don't care how lopsided it is. As long as your labels are correct, you're good. But this would be a density curve for that relative frequency histogram on the left. So we've kind of smoothed it out, we've taken the shape, and we've gotten rid of all the bars. Again, I'm not ever going to ask you to go from a relative frequency histogram to a density curve. It will already be given to you as a density curve. I just wanted you to know where it came from. Okay, so that's what this intro part was. So then on the next page, we're going to look at some calculations for just uniform density curves. These are, basically it's worth knowing this, but in all actuality, it's maybe going to be one question on the AP exam on a multiple choice. So like if something has to go in this chapter, this could be the thing that could go and it would be fine. But for this one, what we've got is and if any of y'all have gone through ADHD testing, this one might sound familiar. It says in an internet reaction time test, ask subjects to click their mouse button as soon as a light flashes on the screen. The light is programmed to go on at a randomly selected time after the subject clicks start. The density curve models the amount of time the subject has to wait for the light to flash. All right, so they gave us that picture there. So first thing I did was I drew in a y-axis. And then we need to drop it down. And now this is a uniform density curve. That picture right there, that's it. The rectangle is enough. So one of the things we said at the front on the front page and up at the top is that the area under the curve always is 1. So good news is y'all know the area of a rectangle. You learned that way back when. So there's two ways you can think about area of a rectangle. You can do area equals length times width, or you can do area equals base times height. Technically, they're both right. For this situation, thinking about base and height is a little less confusing than thinking about length and width. However, you can do it either way. Doesn't matter. So we know the area of that rectangle has to be 1. And we can count to figure out how long the base is. So I'm looking on my x-axis, I'm going from 1 to 5, so my base is 4 units long. What we don't know is the height. We don't have a scale on our y-axis. In fact, they didn't even give us a y-axis when we started the problem. But since we know that the area under the curve always is 1, and we know our base, we can work backwards using our area of a rectangle formula to calculate it. So we know the area has to equal the base times the height. We know if it's a density curve, the area is always 1. Our base, we just counted and figured out it's 4. And what we're trying to solve for is h. So just using some old school algebra, we're going to divide both sides by 4. And we're going to end up getting 0.25 for our height. So that means right here on the y-axis, that is 0.25. I highly recommend you write it as a decimal instead of a fraction. I know that is not what you're used to hearing from math teachers, but for these proportions and percents, it's much easier if you use decimal form than if you have to think about it as a fraction. So for most uniform density problems, you have to do what we just did as your first step. Usually they don't give you the height. You've got to go through and figure it out. So then once you have your height, then you can solve different types of problems. So in this case, for letter B, what it's telling us, they're asking us to find what percent of the time, so that means our answer has to be a percent. What percent of the time will the light flash more than 3.5 seconds after the subject clicks start? All right, so if you look at the picture, I went in and shaded at 3.57. So 3.57 is that where that red dot is on my x-axis, and they wanted when it was more than 3.75 seconds, so I shaded to the right. So what they're asking us for is the area of that little piece. So the area of the whole rectangle is 1. I just need the area of that piece. So what we need to do is figure out what our base and our height are for just that small rectangle. Well, the good news is the height is the same. We don't have to do anything new there. So our height is still 0.25. So then what I did is went down to the x-axis and said, okay, how long is this piece? And it's 1.25. So going from 3.75 to 5, it's 1.25. So I went through and used the same area of a rectangle formula, went through and calculated, and ended up getting 31.25%. So what it gave me at first was the proportion, but the problem's asking for percent, so that's why I had to convert it over. And if you look at my drawing, that seems fairly reasonable. That red shaded part is about 1/3 of that rectangle. That seems reasonable. The other way we could go with that is they could ask us to figure out what the percentile is. So remember percentile, we talked about before fall break, percentile is the amount equal to or less than whatever your value is. So in this case, it's asking us to figure out where is 38% of that big rectangle. So they're trying to figure out what data value does that hit at. So we don't know where we're at on the x-axis. All we know is our height, and now we know our area. So 38%, I'm going to convert that to a proportion, so it's 0.38, and then I plugged into my area formula. So area is 0.38, don't know what the base is. My height is still the same height it's been, it's 0.25. So when I do my algebra, I end up getting, right here, I get 1.52 seconds being the base of my rectangle. So this right here is 1.25 from here to here. Problem is, this time, the rectangle didn't actually start till 1. So we have to also include this piece right here to actually get our correct time. So we have to do 1, got dyslexic there. We have to do 1 plus 0.152. And so we end up getting our total time of 2.52. If this rectangle was right at the origin, we wouldn't have to add that 1 on the end. But because the rectangle didn't start till 1, the density curve didn't start there, we have to include that to get our total. All right, so that's all I'd ask you to do for a uniform density curve. I'd either ask you to find the height, I'd ask you to find the area of a shaded part, or I'd give you a percentile and ask you to tell me where it occurs. So those are the 3 types of things that you could see. And that is a very hyper-specific type of density curve. You don't see it very often, but it's a nice way to kind of intro density curves, so that's why we're looking at it. The one you're going to do the most is the normal density curves. And these are ones you've probably seen before. A normal curve is sometimes called a bell curve. So it's symmetric and bell-shaped. The second criteria for something to be a normal distribution is the mean has to equal the median. And then the third thing would be that most data points are close to the center. So most of it is piled up in the middle, and then as you go farther out on either side, it gets lower and lower and lower. A couple of things that you want to remember when you are labeling your diagrams. When you draw these out, you want to include a label that is a capital N, and then the mean, comma, the standard deviation. So right here, these are the symbols for it, and if you need the reminder over here, that's the breakdown. So one thing just to clarify in regards to why number 3 is important. We said symmetric and bell-shaped, mean equals the median. Well, if I gave you something that looked like this, that actually fits the bill. It's still symmetric, and the mean would still equal the median. It would be right down the middle. It's not bell-shaped, and most of the data points aren't close to the center. They're farther to the side. So that's the difference there between the two. That's why all 3 of those are important to figure out what's a normal curve. If we know it's normal, then the empirical rule is a shortcut we can use. We can only use it in specific situations, but when we do, it can be a time saver. That being said, if your brain is too full, let it go. You don't have to worry about it. All right, so what the empirical rule is, it's, a lot of times people don't call it by that name. They just call it the 68, 95, 99.7 rule. So what those numbers mean is that 68% of the data is within one standard deviation of the mean. So the mean's in the middle. One standard deviation on either side contains 68% of the data, which is a lot, over half. All right, then the 95 comes from all the data being 2 standard deviations above and below the mean. So 95% of the data is within that. And then the last one, the 99.7, is 99.7% of the data is within 3 standard deviations of the mean. So that's almost all of the data. So this relationship, along with those 3 characteristics we just said on the front, are what make data normal. If we meet those criteria, then we can say we have a normal distribution. And that's what we're going to spend time talking about on Thursday. So 2.2.3 is how do we tell if the data is normal. The majority of the time, they're going to tell you in the problem. That's how you know it's normal. But every once in a while, we'll get a data set and we'll have to go back and look at it, which for a lot of you might be something that you're going to end up having to do when you are working your calculations for your GradCap project. So we'll get back to that. Okay, so the other thing that you can do with this is you can use it to help you reason your way through some things. So if 68% of the data is within one standard deviation, that means out of 100%, 32% is left over. So the part that's not shaded in that first diagram makes up 32%, but it's both sides. So it means this side is 16%, and that side is 16%. Right? For the middle diagram, if 95% of the data is in between 2 standard deviations, that means there's 5% left. So on either side, this would be 2.5% and 2.5%. And then for the last one, if it's 99.7%, that only means there's 0.3% of the data left. And again, on either side, we have to split that in half. So it's going to be 0.15% on both sides. Cool. Why do we care, Ms. G? Well, if I'm asking you to find the percent at a standard deviation, you can just go ahead and use this shortcut instead of having to use the z-score formula that we'll talk about on Tuesday's notes with 2.2.2. So that's the benefit. It lets you go through and figure it out without having to go through all that other stuff. So strategy to help you solve these, no matter whether you're using the shortcut or not, if you're using the formulas like we talked about on Tuesday, you want to use these 3 steps. First thing you want to do is draw it. If this is the AP exam or it's a test for me, you got to make it pretty. Making it pretty means you've included the mean, 3 standard deviations on either side, and you've shaded it. If it's homework or it's practice, get the mean, get your data point, and do your shading. And I'm less stressed about the 3 standard deviations on either side. Just get it in the right spot and you're fine. You're going to do your calculations, and if there's work to show, you're going to show it. We'll get into detail about what specifically College Board wants to see a little farther on, but make sure that you're showing that. And then the last part, like always, got to answer the question in context. What does that number mean? Use units from the problem and use whatever the situation is. So we're going to look at a couple quick ones based off of this situation. So this first one, it says the length of human pregnancies from conception to birth approximates a normal distribution with a mean of 266 days and a standard deviation of 16 days. All right, they're not ever going to ask you to calculate the mean and the standard deviation. They'll give it to you. And then also what I've highlighted there, they told us in the problem this is a normal distribution, or it approximates one. So it's close enough that we can go ahead and use it. So they've established that we can go ahead and use that 68, 95, 99.7 rule. So I've added in my label, and I've added in some units to my x-axis, both good practice, always good things to do. So for letter A, it's saying a pregnancy lasts 298 days what percentile is this pregnancy at? So percentile is what our answer needs to be. So of our choices, it's either going to be percentile, percent, or proportion. So in this case, they're asking for a percentile. We measure percentiles. We talked about this a few minutes ago. Remember, it's everything below or at the same data point. So if I'm shading my diagram, I'm shading everything to the left. I want to include all of that except that little bit past 298. So 298 is 2 standard deviations above the mean. So that means this piece that I'm drawing right now contains 95% of our data. And then we just looked at on the other page what the other 2 sides were. So there's 2 ways you can approach this. You can say, okay, well, I know the inside is 95%, and I know that this is 2.5. So I'm just going to add those together. The other way you can approach it is, I know all of this is 100%. The little bitty piece that's not shaded is 2.5. So I'm just going to do 100 minus 2.5. Both work, both are valid, it's just 2 different ways of approaching the problem. And so this is the shortcut. If you were in class on Tuesday or if you watched Tuesday's video, we're talking about z-scores otherwise. We don't have to do z-score in table A. We can just use the shortcut if what they're asking us for is at one of those 3 standard deviations. So that's the shortcut. For letter B, it's asking us what length of time marks the shortest 16% of all pregnancies. All right, so to start with, we don't actually know where this is. They're asking us to figure out, okay, where does that yellow shaded area stop for it to contain 16% of the data? But if we think back, 16% was what we had on either side of 1 standard deviation. So if 266 is my mean, 1 standard deviation on either side would give us 68%. So if we're just finding the shortest 16%, we know that has to be at 1 standard deviation below the mean, which is our 250 days. All right, so that is a speed run through Monday's notes. There are, on the next page, this is on the completed notes on Canvas. I went through and drew out the different types of density curves, gave you the empirical rule one more time. Again, it's helpful to memorize, but it's not required because you can always do the calculations to figure this out. And then there is some couple of practice problems here on the Check Your Understanding. The first one's a uniform distribution. The second one is approximately normal. The answer key to that is on Canvas in the completed notes. So if you want to try those and check yourself, go for it. I hope this was helpful. If you have any questions, let me know. I will see you all later.